To consider this question I've asked about the log scale, there's one simple thing that you should keep in mind, and that's the key to everything. The way you construct a log scale is that linear distances, and by that I just mean regular distances, and the kind you measure with a ruler. The same amount of space is counted the same way. 5 units is half as much, 10 units is twice. It's just uh, measuring distance in the way you've always have. That linear distance is not the way the numbers are marked, but it represents the exponent of the base that produces those numbers. So the base here is 10. This is a base 10 log scale. It's according to the common log. The base is 10. It shows all the values of 10 raised to a certain exponent between the exponents of 0 and 1. The highest number written down is 10. 10 to the first power is 10 because anything to the first power is itself. The lowest number written down is 1. 10 to the 0 power is 1 because any number at all to the 0 power is equal to 1. So this is something like a table with two columns. One column of the table is not written down as numbers, but is there as distance that you could measure with a ruler. And I have crudely drawn in red an approximation of a ruler. I mean, let's suppose the distance between 0 and 1 is 10, 1 and 10 rather, is 10 centimeters. You can measure that with a ruler, and I've roughly drawn that in. That one column of this table is not there in numbers, it's there in distances, and you could calculate that with a ruler. The other column of the table is written in numbers, and that's the numbers on the y-axis, the vertical axis that you see. And it follows the general way we make tables. We've got two columns, and so anything in the same row is a matched value, which is to say, any measured distance is an exponent of the power of 10 that corresponds to the number written down at that distance. So I'm assuming here that there's 1 unit of distance between where the 1 is printed in blue on the semi-log graph. Between there and where 10 is printed, that's 1 unit of distance, and it's in the linear distance there is 10 centimeters. So that's my 1 unit. So that each centimeter mark represents 1/10. So the big mark in the middle would be 0.5 units for 5 centimeters. The the first one is more or less at the 0 point, and the next one up, representing 1 centimeter of distance, it would be 0.1 exponent for 10. And this particular question says, how could you use this little trick of log scales? The exponent as a distance is matched to a number written on a scale. Well, what is a square root as an exponent? Well, it's 1/2. The square root of 10 has the same definition, 10 to the 1/2 power. And we know that if we multiply 10 to the 1/2 power times 10 to the 1/2 power, that would be 10 to the powers added together. That's an old trick with exponents. So 1/2 plus 1/2 is 1. So 10 to the 1/2 power multiplied by 10 to the 1/2 power would be 10. 10 to the first power. And that's according to the definition of square root. What is the square root? It's the square root of 10 is the number which, when multiplied by itself, gives back 10. Any square root has that same pattern. Square root of 2 is the number which, when multiplied by itself, gives back 2. So where is the 1/2 power on this scale? Well, what if you measured half a unit up from 1 to 10? Since the exponents are here, not written down, but in linear distance, and the lowest one is 0, 10 to the 0 power equal 1. And the highest is 1, 10 to the first power equals 1. Where could you find the exponent 10 to the 1/2 power? Well, it would have to be exactly 1/2 of the way between the 0 mark and the 10 mark. And you know how to measure something with a ruler and find the halfway distance. It's particularly easy if you measure that thing and it's 10 centimeters long. I've just guessed that because it seems approximately right, and it's simpler to think about. Where is the midpoint? Where would the 5 centimeter mark? 10 centimeters is 1 unit, 5 centimeters is halfway in between. Where is the 10 centimeter mark? And then you could consult with your calculator if you don't know it already. What's the square root of 10? Does it seem to be in the right place? But if it's not clear, go back to definitions. A log scale has the exponent of its base, and here the base is 10. But it represents that in distance rather than in an exponent written down. The numbers written down are the power that the base to that exponent would give you. So 10 to the 0 power is written at the bottom of the graph, the 0 mark on the graph, and it's correctly labeled 1. 10 to the first power is all the way at the top. We're assuming 1 unit between bottom and top. 10 to the first power is 10. The square root of 10 is halfway in between. And where's halfway in between the distance? And if you get that, you could work out how you could do any other power between 0 and 1 of 10. If I go here to about 1 centimeter, that would be 1/10 of a unit. What would that be? 10 to the 1/10 power. What does that mean, 10 to the 1/10 power? Well, it would be the 10th root of 10. That is what number multiplied by itself 10 times gives back 10. Well, it would have to be more than 1. If it were 1, then you could multiply it by as many times as you want, and you never get anything but 1, so that's too small. If it were even smaller than 1, when you multiply by itself, it would get smaller and smaller and smaller. Farther away from 10, that wouldn't do, so it would have to be greater than 1. But it couldn't be as big as 2, because 2 times 2 times 2 times 2 is already bigger than 10. And that's just 4 times multiplied by itself. So if you multiply 2 by itself 10 times, you get a rather large number. So it would have to be somewhere between 1 and 10. You could think, well, is what I say plausible? That if I measure 1/10 of the distance, I get 1/10 root. Somewhere around here, I'd have 8/10 of the difference, 4/5 of the difference. And could that represent 10 to the 4/5 power? And I think if you stick to the definition, if you stick to the one key fact, and you think it through, you'll be able to work this out. And that will also help you work out the other question, if we extended the log scale to the next rank. And if you put another unit up on top in the y-axis direction, this arrow is pointing up. If you put another unit of distance, then what would be the number to mark at that unit of distance? Well, to keep to the principle, you would want to put 10 to the second power. That would be where 2 units of distance are. Take the linear distance, treat it as an exponent, put the base 10 to that exponent. You'd get 100. If you wanted to do something to find the proper place for a number between 10 and 100, where would you put that? Well, it seems that the numbers can fit the same pattern in distance. That the numbers marked could be as they are now, the big gap between 1 and 2, except in that next rank it would be the distance between 10 and 20. Smaller gap between 2 and 3, except in the second rank, when you're doing the second unit of distance, 10 going up to 100, you would mark that as 20 and 30. So you could take what's there and measure it off against the second unit of the graph, if that was the problem you were working with, how to expand what you've got here.
Now, for this related question, the answer is fairly simple. If you wanted to extend the graph and you use the distance there between 1 and 2 to draw the y-axis higher, and I've illustrated that just by making a copy of the graph and pasting in the duplicate up there to measure the distance. Where would you get? Well, the correct answer, not much good without the explanation, but the correct answer is that you'd get up to 20, and we can get a little closer to understanding by saying on the lower rank, the old graph, the distance between 1 and 2 doubled the amount. So 10 to the 0 power is 1. We could figure out where the 2 needed to go by using a calculator. What is the common log or the base 10 log of 2? We measure up that in our unit. It's about 0.301, and that would be just a little bigger than 3 centimeters in the unit we're using. If we went that same distance above the 10 mark, then again we'd double 10, and that would bring us up to 20. Now, why does that work? Well, for that it helps to remember this old rule of exponents that, as I said before, if you're multiplying two numbers which are the same base to a certain power, so 10 to the a power times 10 to the b power, then what you get is 10 to the a plus b power. So if we've got 10 multiplied by 2 to give 20, that's 10 to the first power times 10 to the power of the log of 2. That's by definition. That would be 10 to the first times 10 to approximately the 0.301 power. Put those together, you get 10 to the 1.301 power is 20, and following our scheme that you measure exponents as the distance and mark the numbers as the powers of 10. By copying the distance from 1 to 2 from the bottom, to the top, you